Okay, I'm going to take a look at example 4.1, and this is you have two vectors and you want to add them together, and there's two approaches. One is using parallelogram law, part A, and part B is using the component method, okay, which is really the method where you apply the unit vectors, okay. All right, so let's go out and take a look at this first, and I'll describe kind of the process here as we go through it, and I'll kind of scroll back and forth between them. But let's say that here are your two vectors. You have a vector B and vector A, okay? And here's the x-axis, positive x-axis, and there's an angle between each of the vectors and that axis, okay? And that's one way to represent a vector uniquely, okay? So the next step, what you do is you take and basically you create a parallelogram by doing a head-to-tail method, or tail-to-head, or however you want to say it. Tail-to-head, let's say, so you take this vector and stick it right on here, and then you take this one and put it right here, and they'll meet at the end. So these are like, this is like the vector A being placed here, and this is vector B being placed here, okay? So that's the first part. You're creating this parallelogram, all right? And our goal is to find this resultant, right? Which is basically the point at which these two, sides, or this side and this side meet, okay, in the corner here, all right? So first thing is that when we take a look at that, we're going to be applying, I'll take a step back here. We're going to be applying, first thing we'll do is we'll find the law of cosines and then the law of sines, okay? So we can actually use the law of cosines to find the magnitude, okay? So if you remember from previously, that if I go back to the slides, here's a law of cosines really, and it relates the sides, right? So what we're really doing is we're going to do the square root of both sides of the equation here, okay? So we can figure out an angle, and then from that angle we can determine the side, okay? So what we're going to do in that first problem is we need to figure out what this angle is, C, okay? And then we can apply this to actually find the magnitude of the resultant. So going about this, where like we said, we'll apply the parallelogram law first. So 6 and 8 squared, 6 squared, 8 squared, those are the two sides. Then minus 2 times 6 times 8. Okay, that's just like A and B. This is kind of like side C. This would be A, this would be B, this would be minus 2 times A times B times cosine times an angle. And this angle is going to be opposite the side C. Or in our case, going forward here, this is kind of like our C, okay, from the equation, right? We just replace it with R. So what we need to do is determine what this angle is right here, okay? The first thing we can recognize from looking at this diagram, without knowing what this angle is, the magnitude of this angle is that this line and this line are parallel, and this line and this line are parallel. So what's going to happen here is that as a result, this angle and this angle are going to be equal, okay? So from that perspective, we know that these two are equal. And we also know that all the angles inside here are 360 degrees, okay? So this is going to be equal, this is going to be equal. We only know that first it's 360 minus 2 times something gives us that angle, right? Okay? Divided by 2, right? So what we recognize is that this angle and this angle also follow the same idea that, the sides are, you have two parallel sides here and here and here and here. So the angle from here to here is going to be the same as the angle from here to here, okay? So what we could say is that this angle and this angle together are just going to be half of the total. Okay, so these two together, we don't know what the number is yet, but this angle right here and this angle here is going to equal 180. Okay, so the next step, what we can do is, if we look at this, we know this is 60 here, and we know this is 15. This was given. So the 45 is just coming from 60 minus 15. Okay? So now I know this is 45. I know this one is 45. Okay? And if I take those two together and subtract it from 360, I would have the remaining two angles, right? This angle and this angle. Well, we also recognize that since this angle equals this angle, we can just do a divide by 2 to come up with the answer. Okay? Or you could have written it out, 360 minus 2 times 45 equals that. Or 180 minus 45 gives you the 135. Okay? It depends upon how you want to look at it. All right? But the equation just becomes, and this is the same way you do it every time when you are doing a parallelogram approach. So it just becomes 360 because all the angles inside of parallelogram together equal 360. And then minus 2 times 45 because there's one angle over here and one angle over here. So that gives you, what's left over is 270, right? But they're two angles and they're both the same size, so we just divide by 2. So now we have 135 degrees. Okay? So the angle across from this resultant is 135 degrees. So that's where this comes from. So all you do is plug in and solve this equation, and now we have the magnitude of the resultant vector r. So we have essentially the length of this vector. Okay? That's the first part. The second part is we need to have another measure, right? That gives us the length of the vector, but now we need to know something about the angle. Okay? So the author chose to use that as psi here. So we have an angle right here. Call that psi. Okay? But the first part, what we'll do is we'll just basically look at it from the perspective of a triangle. So now we'll ignore this top part and we'll just take this triangle basically made from here, here, and here, okay? So when we have that triangle, now what we can do is we can apply the law of sines, okay? And what you recognize here is that, hey, I have an angle here. I have a side. I have a side over here, and I have a side over here. So what I could do is I can use that and the law of sines to actually figure out like what is the remaining angle, which would be like theta here. Okay. So if we do that, go back up here. And however we do it, like in this case, here's my, like if you want to think about it, here's like r, here's the angle opposite r is equal to like side vector, which was the 6. I think the 6 was, the b, vector b sine of theta over that, okay? Which is theta is, of course, like I said, theta is the angle opposite this side here, which is the b, or size is 6, okay? So now when you get that, you can solve for theta, and theta comes out to be 19.1, all right? So going back here, this now becomes 19.1. So to determine the angle from here to here, that this the arc of this arc goes across, you just add this one to 15, and that gives you the angle. And so now going back up here, here's the 19.1 plus 15, and it's 34.1 degrees. Okay, so now you have the magnitude and the direction, or essentially the angle. Okay. Okay. So the second part of this, that's how you would get it if you're using the parallelogram method. We can also do it with a component method. Okay. So what we can do is now we're going to use like the cosines, or cosine functions, right? And first part of it is breaking these up into their components, their x and y components. Okay, so first thing is we do is you can look at it. You have a side here, so it's like if you wanted to get vector A, you go along the x all the way out to here, and then all the way to the point that's perpendicular to this, and then you go straight up, and this gives us the y part. So this is ay. Okay, and we do the same thing for by. Here's our for b. Here's our bx. And here's our by. Okay. Now we can just use those trig functions to solve for each of the components: the ax, ay, bx, and by. Okay, so just go back to the slides briefly. And back from the slides, what you can see is that, let's say we have a vector, either this is our a, this vector is our a or our b. It really doesn't matter what vector it is, but the adjacent side essentially is our x in this case, and the opposite side is our y. Okay, so if we're looking for the hypotenuse, or I'm sorry, if we're looking for the opposite side, that's our y, it would just be hypotenuse times sine of a equals the opposite side. If we're looking for the adjacent side, it would just be, take this, bring it over to the other side, be hypotenuse times cosine of a is equal to the adjacent side. Okay, so it's just algebraically manipulating these equations. All right, and that's really all we're doing for that first part. And the last one we can take a look at is the tangent. So if we wanted to find the relationship between the adjacent and opposite side, we'd do the tangent of this angle, okay, or the ratio of the two. Okay, so that's all I did applies. Here's like the adjacent side, a times cosine of 15. Here's like the opposite side for that vector. Here's like the adjacent side. Here's like the opposite side for that vector. Okay, so now we have the components. We have the x components, which are these two, and the y components, which are these two. So basically it says like you do these separately, right? You just add ax to bx, gives you something over here. Then you add ay to by, which gives you something up here, and then your new one comes out to be somewhere over here, right? Okay, that's our r. All right, so we continue on. And this is how we would write it with unit vectors, right? So it would be ax is b times this unit direct vector I, which is a magnitude of 1 in the direction of x, and ay, which is a magnitude of 1, I'm sorry, ayj, which is a magnitude of 1, the j is, in the direction of ay. Okay, or in the direction of y, and then the same thing goes for here. I is a magnitude of 1 in the direction of x, j is a magnitude of 1 in the direction of y. And to get the magnitude of that portion of the vector along that direction, you just multiply it times that scalar. Okay, so here we have our two vectors in terms of the unit vectors, okay, or in our component form. All right. So when we go and add them, what we need to do is we'll come up with a resultant Rx and a resultant Ry. So we add the x components, and then we add the y components. So the x components times I, and then the y components will be added together, and there'll be times j. So the end result is 10.7274, whatever. Quite a few. How many significant figures we have here? 6. Okay, and the end result is 4 significant figures. I don't know if the author said that, but it was written in 4 significant figures. So now we have our two components, and we just apply Pythagorean theorem to come up with the resultant vector, which is basically, the distance. So it's just this component squared plus this component squared, square root gives us 12.96. And then we can apply the tangent, right? The tangent was and you could have used sine, cosine, it really doesn't matter, but we know we have this relationship which basically says the opposite side equals the adjacent side times the tangent of that angle. Okay, we can rearrange this equation, so that it just becomes, ry over rx, inverse tangent, both sides. Then we come up with inverse tangent of ry over rx. We solve for that, and we come up with 34.1 degrees. So the nice thing here is, of course, we had two different ways essentially to come up with the same solution to this answer. And as an engineer, it's good to be able to have another technique in order to find it. Okay, so that's pretty much it for this problem, and it's a good one to look at. For any parallelogram problem, you'll see like adding two vectors. You'll use the same approach each time. Now, you might think, well, what if I had to add 3 vectors or 4 vectors or more? The parallelogram approach, you can only do 2 at a time. So you'd have to do like 2, come up with a result, and then do that resultant with another vector and do it again. So it really could get to be really cumbersome, as you get number of vectors increases. The component approach is far superior to that, and that's really, we're going to, even though we look at the parallelogram law and we look at solving a problem with this or a couple of problems with this, it really is an inferior approach, although it is kind of nice to have another way to verify um, your results. Okay. But from here on out, afterwards, you'll see that, as you take courses later on, this approach might be explored just for interest and showing you kind of how another way you could do it. But the preferred approach is the component method approach. And that is all for this problem, for solving it with parallelogram law and through the vector component approach.